Dr. Barth, how are you doing? Dr. Barth. Dr. Barth can't hear me. Dr. Barth, can you hear us? Dr. Barth, can you hear us?
Are we live, Paul? Because I'm not
Yes.
getting any sound or audio this side.
Golly, I don't know what happened. It, you're on. Yes. Go.
I'm going to assume we're live, and I'm going to go ahead and get started. Welcome, everybody, to episode number 68 of How Do You Know, our first episode of 2023. So welcome back. Hope you all enjoyed your holiday break. I certainly did. And we've started the new semester here. So as is our tradition, we go ahead and start with a new set of episodes for How Do You Know? And of course, as always, our program is brought to you by Star Mentor. This is the most exciting book. If you've just gotten a new telescope or pair of binoculars for the holiday, this is your ticket to adventure and learning how to explore the heavens, learning how to guide and use your new instrument, and how to participate in discovery. It's a wonderful book if you have a friend to work with, or if you're being asked by a new astronomer to help them learn. So let's go ahead and get started today. Today's episode, Searching for Mega-Tsunami. And we want to, before we get started with today's topic, we want to talk to you about an exciting project. I've been working with some professors from other universities, and we've decided to launch a project that we're calling the Eratosthenes Project. And we're going to help you take a walk with ancient astronomers. It's really fascinating. Ancient astronomers and mathematicians from thousands of years ago, the classical Greek period, and across many civilizations in the Mediterranean, working with just a ruler and a protractor, they were able to make amazing discoveries. They were able to prove the Earth is round, find out the relative distance to the Earth, and from the Earth to the Moon, and from the Earth to the Sun. They were able to work out a mathematical model for the cosmos. And one of the most interesting things I encounter as an educator is that oftentimes my students like, well, those people were silly. They didn't even know. And they go on about their limitations compared to today. But it turns out these folks were really, really brilliant. And we want to invite you to participate in the first Eratosthenes project. And that's going to be coming up in March. And we'll have more details for you as we go through. You'll be able to build your own simple instrument and collect some data. And you're going to be able to participate with us. And you're going to be able to help us measure the Earth. And International Measure the Earth Day, it's actually going to be Measure the Earth Week, which will occur in mid-March of this year. And it's going to be very exciting for all of us to participate in. And we'll be talking more about that. Let's go on today and talk about our topic for today. We're back on Mars today. And one of the things that we discovered on Mars as we got closer and finally put a spacecraft down on that planet, the two Viking orbiter and lander pairs that flew there in 1976, And they took high resolution photos from orbit for the first time. And the discoveries from the Viking were really incredible. And not only from the Viking orbiters, but the Viking landers. And we kind of lost our innocence when Viking went to Mars. We had many romantic ideas and lots of blurry pictures that were fun to look at from the probes that flew by at tens of thousands of kilometers per hour. But in fact, Viking gave us photographs from a couple hundred kilometers above the surface from a stable satellite in orbit about Mars and relatively high resolution compared to earlier cameras, much higher resolution. And we got to take a look at some interesting features that we're still figuring out today. And part of our show today is talking about killer asteroids, which we've talked about before. Everyone's famous and favorite topics. Scott Roberts from Explore Scientific and I had a conversation the other day, and we were talking about, oh, look, I have a meteorite. Oh, gee, what about killer asteroids? And the conversation just goes to these mega impacts because they both horrify and fascinate us. If you're interested, go back and take a look at How Do You Know number 65 about new planet killer asteroids that we've discovered just this last 12 to 18 months. And of course, episode number 63 about the DART impact. Can we, in fact, take an asteroid and deflect it, change its course? But it's good to keep in mind, we kind of tend to be egocentric that way. Earth is not the only target for killer asteroid impacts. So why do we have these things anyway? It turns out that when you're putting a planetary system together, this is a process called accretion. And simply put, solar systems are built up from collections of very tiny particles. Basically, as a nebulae condenses and cools off, we'll find that various regions cool down. And the regions closest to the star, we have metals can condense there a little farther out, silicate type rocks, and farther out we have ices and dust from stars, simple molecules of carbon and nitrogen and oxygen. These small particles collide very, very gently, and they stick together mostly because of static cling. If you ever pulled a sweater out of the dryer and it sticks to you, or maybe you walk by somewhere in our house, what happens is the dog comes up and wants some attention, and then static cling, and we have all this stuff the dog has on him collecting to us. So this static cling is this very gentle process, and you think, oh, how nice, little particles colliding, and there'll be planets one day. But the pieces get bigger. And if someone throws a dust bunny at you, that's a lot different than if someone throws a shot put at you. And that's a lot different than if you get hit by an automobile. And it's much the same process. As the particles get larger, they eventually become things called planetesimals. We're now talking, they accrete, and up through the stage, we know we have a lot of asteroids, which are what's called rubble pile asteroids, collections of small rocks and gravel and sand particles. And the density is rather low, and they're not actually forged into a single rocky silicate structure, but rather just literally a pile of small particles, a gravel pile or a rubble pile. Eventually, these objects get bigger, and somewhere they cross the 500 to 1,000 kilometer diameter threshold. And at this point, they become objects with gravity intense enough, number one, that the pressure at the core becomes very high. And secondly, the objects are so large now that natural radioactive decay, which produces heat, isn't able to escape easily. The outer layers of this object become insulators. and hold that heat in. And between the heat and the pressure, the core melts, and the object does two things. It fuses itself into a single silicate solid object. And secondly, we have a situation where it crushes itself into a sphere and it becomes a planetary body. When these bigger objects collide with planets or with each other, the objects, as they get bigger, the impacts become more violent. And maybe you've all seen the science fiction classic When Worlds Collide, produced by George Pal, a wonderful film. Others in the genre, Deep Impact and Armageddon. I think Deep Impact is with Elijah Wood is one of my very favorites. It's quite accurate. And when we talk about that, we talk about impactors in terms of kinetic energy. And simply right from the root word, kinetic energy means energy of motion. How much energy does something have because it's moving at you really fast? So if we have a small object, and I have here a ball of clay, this is perhaps 100 grams, and could this hurt you if it hits you? Well, it depends very much on how fast it's moving. If, I were to wind up, I can throw a fastball at about, maybe 60 kilometers an hour, maybe, and that might sting, but it's not going to injure you. On the other hand, if we put it in a cannon and we fire it at you, now it's moving perhaps 1,000 meters a second. Now it's a genuine danger. If we put this in orbit, you realize we track things this small in orbit. Why? Because if this is in orbit, it's now moving at, 17,000 kilometers per hour to stay in orbit around the Earth. You're talking a terrific velocity. And if something is coming anti-orbital, a satellite in one direction and a piece of debris in the other, then the impact is really catastrophic. And at these speeds, orbital speeds, it doesn't matter if this is solid, if it's liquid, if it's plastic, like this clay is deformable, I can squish it with my fingers, or if it's solid, like a piece of rock or metal. Essentially, all we're worried about now is the kinetic energy. Half of the mass times the square of the velocity. And if we're talking 10,000 kilometers per hour, and then we square that, that's a really large number, friends. And we're going to deal with mass in kilograms and velocities in meters per second. And if you're moving 1,000 meters per second, 1,000 squared is 1,000,000. And if you're multiplying by 1,000,000, you don't have to have a very large mass to have a really large impact energy. So how large a whack is that when we're talking about an asteroid? Let's talk about something, let's say 5 kilometers. And you might say, well, how many 5-kilometer asteroids are there? And the short answer is we don't know. We discovered, 2 new 1-kilometer class asteroid, one a little less, one a little more, just this last year. And they're Earth-crossing asteroids. They orbit inside Earth's orbit, and they come toward us out of the sun, and they're really, really difficult to spot. The other thing is we could get something falling in from the Kuiper Belt, and something that far out, say 40, 50, 100 AU, an object out there, it's so dim, it's so dark, it moves so slowly, it's really difficult to pick up. And so something like this falling in, I'll remind you that the Chelyabinsk meteor, which came down in 2013 and exploded over the city of Chelyabinsk in Siberia, in Novosibirsk, in Russia. And this thing detonated over the city with a 500 kiloton blast that damaged buildings and injured many hundreds of people and blew out tens of thousands of windows We never saw this coming. Matter of fact, the odd thing is, we were looking for an asteroid to fly by the Earth that day, and this thing appeared out of the dark, and it was as large as, say, a two-story house. It was a big object, 10 to 25 meters in diameter. We had no idea it was coming. Had something like that, instead of coming at a very grazing angle where it flew into the upper atmosphere and exploded, had that come down more vertically and struck, that would have been what we refer to as a city killer, and that could have wiped the city of Chelyabinsk right off the map. An impact like that on a major city like Tokyo or New York or Berlin would kill tens of thousands, perhaps hundreds of thousands, and billions of dollars and euros in damages. So, and that's something as large as a house. To say nothing of the impact at Tel Al Hammam, the biblical city of Sidon, which was hit with a rock in that class, and it was absolutely destroyed. At impact, temperatures went up to about 3,000 Celsius, to the point where metal objects were melting, and people just and buildings just disappeared. But if we consider a 5 kilometer asteroid, let's consider a big one, 5 kilometers, 5,000 meters. In terms of hills on the Earth, a 5,000 or 5 kilometer peak is a sizable mountain, but it's not by any stretch of the imagination exceptional. There are lots of places bigger than that. Well, if we consider this to be made out of porous rock, like sandstone, say 3,000 kilograms per cubic meter, this modest 5 kilometer asteroid, which is going to be irregular, shaped like a potato, it's not anywhere near big enough to crush itself into a sphere. This thing has a volume of 65 billion cubic meters, and it's a mass approaching 20 trillion kilograms. In terms of regular human understanding, things like how much does an ocean liner or an ocean tanker weighs? How big is a building? How massive is a bridge? And in terms of things that we can do and build, this type of an object is far beyond our experience, and it's going to be approaching at, say, 40 kilometers per second. This is an orbital velocity. Something like this gives us an impact energy, friends, of 38 million megatons. Nobody's lobbed a megaton weapon in anger. The biggest nuclear weapon exploded in anger is about 20 kilotons. The very biggest bomb any fool ever built, known as the Tsar Bomba, was built by our Soviet friends in the Soviet Union era, and that was 50 megatons. They dropped it on an island, which pretty much isn't there anymore. And there's a bit of it left, but it devastated that island. And you're talking 765,000 50 megaton bombs. It's insanity. And this thing comes streaking in, and all that energy is liberated in a time period of a few moments. So, what do you do with that much energy? If you're a planet and you get whacked, what happens to all that energy? Indeed, when a big asteroid hits a planet, it makes a very deep crater. The crater may go, for something like this, would go kilometers deep, and it would be cone shaped. But the cone is very unstable, and gravity causes the sides to collapse in. Think of digging a hole in wet sand at the beach. You can dig it down so far, and then the sides start slumping in. So you end up with a crater which is wider and shallower. But that's not the first thing that happens. People think, oh, right away the crater is created. No. The first thing is the asteroid vaporizes. Think about this for a minute, friends. You think about, oh, I'm going to make some pasta for dinner. And so I'm putting on a pan of water, say 3 or 4 liters on the stove in a big pan. And if you forget and you come back and the pan is boiled dry, how long does that take on your gas or electric stovetop? That takes quite a while to vaporize completely 4 liters of water, a gallon for our American friends. Well, if we think about that, this 65 million tons of rock and other materials is vaporized in less than a second. The impact just turns this rock essentially into gas. And in terms of the impact, that doesn't matter at all. It just doesn't matter. It turns out that this uses only a tiny fraction, a few percent of the total energy of the impact. And the material inside the crater, we think of craters having ejecta, where, oh, here's this crater and material has been blasted out of it and has rained down upon the surrounding area and covers it with a blanket of stone and dust. And yes, that's horrific, but in fact, much of the interior material of the crater is also vaporized on impact. Only a small fraction lands on the ground as ejecta. Think of dropping an egg on your kitchen floor. I know eggs are expensive today. You would probably weep a little bit. But think about just dropping an egg on a hard kitchen floor, tile or wood, and the egg hits. And of course, what happens? Which way does the egg go? Does it go up? Maybe some. You may have a few droplets on the side of your cabinet or fridge, but most of the egg will go outward horizontally. Most of it splatters outward. And essentially, that's exactly what happens when an asteroid hits a planetary body. These planets are essentially rock. If you're talking about the Earth, the Moon, Mars, Venus, Mercury, these are kilometers thick stone mantles if they have an interior liquid crust at all. And this impact hits, and most of the energy is directed outward. If you want to experience this and not drop an egg on your kitchen floor, you can try dropping a water balloon onto a clean, dry asphalt or concrete surface. You'll get much the same situation. So, we're talking mega tsunami today. What happens when an asteroid hits the ocean? You realize if a 5 kilometer asteroid were to strike an ocean on the Earth, the average depth of the sea on Earth is something less than 3 kilometers. Most places, the asteroid is this size is bigger than the ocean is deep. Most places on the Earth. On Mars, we believe quite strongly, we have a lot of evidence that Mars had ancient oceans. We're talking 2.5 to 3.5 billion years ago. These oceans were probably mostly on the order of some hundreds of meters deep, perhaps a kilometer, but certainly not more. And when an asteroid like this hits a body of water, the destruction is even more effective than if it hits the land, because a great deal of that energy will be destroying water by vaporizing it. It's not going to splash like throwing a brick in a mud puddle and you get a big nasty splash. No, this is going to vaporize the water on impact. So you're talking about vaporizing, oh, some hundreds, perhaps thousands of cubic kilometers of water. That's going to go into the atmosphere and outward as a huge steam explosion. And this blast wave is actually going to peel back the surface of the ocean. If you think of the asteroid hitting and the water through this blast and steam pressure just being peeled back and stripped off the land and hurtled outward in all directions. Now, if we're talking a kilometer deep ocean on Mars, this is going to be the worst tsunami ever. If you've looked at video from the tsunami in Fukushima, Japan, or perhaps the one in Indonesia in Christmas, I think it was 2006, those tsunami came on and people stood and looked and went, wow, look at that big wave coming in. And the wave came in at perhaps 20 or 30 kilometers per hour, and it just kept, a lot of water kept surging inland. This is not what we're talking about at all. That's a very gentle splash, splash, your friend in the pool sort of a tsunami. This sort of wave, because of the huge blast pressure behind it and the steam explosion behind it, this wave is going to peel up and it's going to be traveling at supersonic speeds. It's going to be traveling well over 1,000 kilometers an hour, the speed at which a military jet can fly, faster than a commercial aircraft. If you were in a commercial aircraft and flying as fast as the plane would go, Boeing, Airbus, doesn't matter, that wave would overtake you and destroy your aircraft. What's strange about this is most people don't really understand blast energy. You may have seen, a photograph of, or a short video clip. Oh, here's bang, a bomb goes off and some vehicle gets destroyed in a military explosion. Okay, but how does that explosive really destroy a vehicle? What you're really using is a blast wave of air. When you have a large artillery round that hits and the blast wave goes off, something like this, the blast wave actually puts pressure and knocks things over and rips and tears and destroys metal. From something like this, a supersonic wave, it's going to push the atmosphere ahead of it. The crater area behind will be effectively at vacuum for some seconds because the blast pushes not only all the water but all the atmosphere out. And the water wave is here and is moving across and it's pushing the air in front of it. That air would be compressed to a density greater than that of steel. You're now talking air being compressed, a couple of thousand times until it's this relatively thin envelope of air, but it's at a density greater than that of steel and it's moving 1,000 kilometers a second. It's like a steel wall coming at you at the speed of sound. Horrifying. This sort of a blast wave would strip the ground down to the bedrock. We think, giant tidal wave, giant tsunami coming in to shore, and the wave is going to hit, and the wave of water is going to knock. Oh no. If the mega-tsunami is coming at your coastal city, the city will be absolutely stripped down to bedrock before the first drop of water strikes. That air blast is going to be terrific. And in thinking, well, what's the difference between the compressed air wave moving in front of the tsunami and the water wave itself? It's kind of a mistake to think of, is the air blast more deadly and damaging, or is it the water wave that's more damaging? It's not like that. They just destroy things differently. They're both rather equally destructive. Consider that on Earth, where we all are, water is about 800 times denser than the air. On Mars, even in the ancient past, with liquid oceans, the air still would have been likely thinner than it is on the Earth today. So the density difference between air and water may have been even greater. And even when you consider, this air is compressed to a density greater than steel. Yes, for the first few seconds. But the difference is, friends, of course, that air is compressible and water is not. Think about a stuntman for a film. And they jump off of a building or a bridge or some high place, and they land on a big inflated cushion. And pow! And the cushion is compressed by the impact of the stuntman's body because air is compressible. We can sit on a balloon and compress it. We can pump air into a tank, be it oxygen, acetylene, carbon dioxide, nitrogen, whatever, and we can compress those gases. We can compress gases until they become liquids. That's how we get liquid oxygen and liquid nitrogen, mostly by compression. Okay, but what about water? Water is really not compressible, nor does it expand. It has a very, very tiny coefficient of expansion and compression. And so if you dive off, many of us have done this, dive off the high board or dive off a rock into a pond and you miscue your dive and you belly flop. And that's quite an impact. Why? Because unlike an inflatable air cushion, which compresses, the water is not compressible. It's been said that if you jump into the water from more than 30 meters, it's about as damaging as jumping onto concrete. The water doesn't give way. And so when we're talking about this wave coming at you, the wave expands in all directions, of course, and that air decompresses because it's filling a larger volume really quite quickly. It's not to say that it's a good thing to be within 50 kilometers or even, say, a 1 kilometer asteroid. If you're within 50 kilometers, it's going to be a very bad day and your survival is not very likely. But compared to the size of a planet, of course, 50 or 100 kilometers is a fairly small area. But this water wave, my friends, this water wave continues its speed. And something like this from a 5 kilometer asteroid in a 1 kilometer deep ocean, you're talking a wave which may be 1 to 2 kilometers high. You're talking a wave which is taller than any building, and it's higher than many small aircraft fly, and it's coming at you. It starts out at supersonic speeds, but it's racing across the land, and that air blast will strip the ground to bedrock, everything that's movable, rocks, sand, surfaces will be scoured and abraded. But that water wave hits, and it keeps its destructive power for much, much longer. And this ejecta blanket that we get from an air blast, and we've got a nice picture there, and I think Paul can probably bring that up for us. We've got this lovely image. There it is. This is an image from one of the Mars orbiters, and the one we're seeing on the screen is not near as nice and high resolution. If you go on the internet and you look up JPL images of crater impacts on Mars, this one happened in 2012, and we can see in the center here, there's that bluish region. That's the ejecta blanket, and we can see that it spreads kind of in a fan shape, much more off the top and sides, and that essentially gives us the direction of impact. This was not a vertical impact. If it was, the ejecta blanket would be very symmetrical. And that blue material is rock and gravel material that blasted out of the crater. And if you look about 1 to 2 crater diameters out, you can see a lot of texture. That's because that's rubble and material that has been blown out of the crater. And when you take a look at that, the black streaks, which extend much farther, those are dust, essentially. Those are what we call rays. We see those on the moon as well. And these are rays of dust and things that can go out much, much farther, tens, even 100 times the diameter of the crater. That's our ejecta. But this happened in an arid, waterless environment. What happens when we get a water eroding a surface? What happens when we get this mega-tsunami on Mars? The asteroid strikes we're talking about here, we believe here's a question. Does a gravity wave have mass? Pekka, gravity wave, are we talking about the sort of things where We get gravity waves detected from merging neutron stars. Um, they have energy, so they have mass, but the mass would be infinitesimal. Um, and if we're talking about the water wave, does it lose mass during traveling? Yes, it would, because the water wave would soak into the ground. Some of it would be thrown up as spray and vaporized. And I don't know, Pekka, if you've ever seen um images from a catastrophic flood or a dam collapse. You see sometimes, this was familiar to me as a boy growing up in the Midwest because our rivers would freeze. And then in the spring, the ice would break up and the river would begin flowing very suddenly. I also saw this effect in the desert in Southern California, where I lived for about 30 years. You would get a huge rainstorm up in the mountains, and the water would come cascading down, and the river valleys, what they call arroyos out there, would be dry. But then you would hear a rumbling, and you needed absolutely to get out of that arroyo and onto high ground, because what's coming down is a very sudden flood of water. And in the case of an ice dam, it's carrying blocks of ice the size of automobiles along with it. And in the dry valleys in the desert, you're carrying rocks, brush, trees, debris, and the idea of, oh, I could jump in and save someone. No, this isn't simply a fast flowing stream of water like you would see at a water park. This is water that's full of debris. And when we're talking about a mega tsunami, you're talking about stones, boulders. And if it's a city on Earth, you'd be talking concrete, rubble, debris, all things from human made from that area. But on Mars, you'd be talking about large hunks of stone, certainly as big as buildings, being tumbled along and washed. There's an area in Washington state in the United States. We had an inland ocean covering what's now the states of Idaho and Montana, hundreds of thousands of square kilometers, and it was held back by an ice dam, which one day, as the earth warmed, some 10,000 years ago, as the ice age was passing away, this ice dam broke. And you can see the scars on the terrain today. You can see the huge valley that was carved by the running water, and stones that we can test them. Geologically, they came from hundreds of kilometers away, and we're like, wow, how did they get there? Did aliens transport them? Did ancient civilizations? No, no, no. This was a catastrophic flood. And we were aware of this when Viking landed on Mars in 1976 and started sending back pictures. We started to see some features on the ground, which we labeled at the time outflow channels. And we said, wow, there must have been a really big flood here, because it's clear that water carved this canyon, this valley, and we could clearly see signs of erosion and large blocks of stone which had been moved. And although that's not to say there weren't dry Mars advocates, as recent as, oh, I think 2007 or 8, there were people who certainly well educated who were claiming, oh no, this was liquid carbon dioxide, no water on Mars. No, indeed it was water. And the two impact sites we've found, which we believe have been associated with mega-tsunami on Mars, and the geological evidence of titanic flooding. One is Lomonosov crater. I'm hoping I'm pronouncing that correctly. That one's up in the Martian Arctic. We believe that was the site of a shallow sea 2.5 to 3 billion years ago. This crater, 120 kilometers, 75 miles wide, large enough to swallow most urban areas. The impactor would have been 6 to 10 kilometers wide, much like the dinosaur killer impactor that wiped out the dinosaurs on Earth in the Chicxulub impact 65 million years ago. This is much earlier than that. And the Lomonosov impact, This would have inundated about 800,000 square kilometers or 300,000 square miles. If we're talking Europe, that's an area, I believe, larger than France. If you're talking a strike in Central Europe, somewhere in Germany, um, yeah, in a shallow sea in that area, you're talking about inundating an area that's just enormous. Pole crater, and Paul has given us an image. We'll talk about that in a second. Pole crater, named for science fiction master Frederick Pole. That bad boy was 69 miles wide, or 111 kilometers. This one was in the Maha or maybe it's Maja Vallis, sorry, near Chrysoplanetia. This is the one that Viking discovered in 1976. It was originally called an outflow channel. And Paul, go ahead and put that image back up, if you would, please. We'll see this image. This is what we call an outflow channel, friends. And you can see here clearly the flow was in the direction from the bottom of the photo toward the top. And if you look at the two impact craters that are lower down in the picture, those absolutely show a teardrop shape. Why do we have those shapes, and why are they there? And why are there conspicuous craters there? If you think about an impact crater, and these two impact craters would have predated the flood, these impact craters have raised rims. The impact strikes, penetrates the ground, and that enormous impact pressure lifts up rims, which we know from the moon, these very large impacts. These rims can be 3 to 5 kilometers tall. These can be substantial barriers in terms of an oncoming flood wave that may have been a kilometer or so high. And we can see where it must have been fascinating. And one can imagine it would have been, if you could have some sort of a drone hovering, say, 500 meters above the crest of the rim as this wave came along, and to just see the wave break over these craters. They must have been filled with water for quite a time. And the material, the water flowed around them. If you've ever seen water flowing around a bridge pylon when the river is at flood stage, and you can see the pressure wave on the upstream side, and you can see the turbulence on the downstream side. And essentially, this flood wave carved away the valley, but the harder rock that was lifted up from the planet's interior that made these crater rims resisted the flow, and these formed these teardrop islands. And when we spotted these in 1976, people immediately cackled with glee and said, "Wow, flow islands." And they realized this meant there had been at some time liquid water on the surface of Mars that flowed across the surface. And at the time, I don't think you would have found a single scientist or engineer who was thinking enormous asteroid impact, gigantic tsunami. We were thinking of something more Amazonian, like a large river which flowed for millennia and carved this valley slowly, something like the Grand Canyon. But no, this was likely carved out in a very short period of time. How long the flow would have continued, days, perhaps weeks, but not that long on early Mars. The water would have flowed and then either flowed into a new basin, or some of it may have surged back. The third impactor, the one that you see in the center. Paul, could we put it up just one more time, please? That image. There we go. Thank you, my friend. If we're looking at the center, this is what was originally referred to in astronomy books as a splosh crater. This crater would have been later, indeed, than the first two. And you can see what looks like to be mud flows from that crater flowing outward. And essentially, that's what it would have been. All this water would have saturated the ground. And given that Mars is quite cold, it's likely that all this water then froze beneath the Martian surface and could have remained frozen in a permafrost layer for millions of years. But at some point, another impact hit, and that impact would have melted the subsurface water and created mud flows. And you can see how these mud flows flow on top of the tail of the leftmost flow island, and they flow up the slope of the right flow island. And this would have been just a horrific pyroclastic mud flow that would have inundated everything around it. So when we're talking about this, how far away was the asteroid impact from these flow islands and the Majavalis? Well, the pole impact crater is 900 kilometers away. So you think about it. Oh, I'm safe. I'm 900 kilometers. Think of something 900 kilometers away from you. And so I'm thinking, what? Maybe where I am in Northwest Arkansas, maybe Atlanta, Georgia, or Springfield, Illinois, something that, and no. Mont, hoping I'm saying that right, Becca, Mont, southern roundish rocks in Sweden are pushed from almost the northern circle during the ICU time. Finland, one of the oldest meteoroid crater that produced lake, and I'm not even going to, my friend, I'm not going to try that one. In the whole earth, I did my swimming lessons on that very water. Yes, wonderful. You are swimming in an asteroid impact, Becca. That's terrific. I love that. Yes, that's something I'd love to do. We had moraine lakes up in Wisconsin where I grew up, which in fact were glacial lakes. Harold is saying hello. Harold, so glad to have you back with How Do You Know this new season. So we're talking about this kind of crazy osmosis is with us. Love it. Greetings. We're talking about this kind of an impact and this kind of a devastating flood. Mike Wiesner, When Worlds Collide. Yes, one of my favorites. We'll talk about that in a minute. 900 kilometers away, and you're talking about eroding away mountains worth of material and carving a valley. Mike, thank you. Starmender is a wonder book. Love it, my friend, and thank you so much. These flow islands, we had these on Earth. Trust me when I tell you the Chicxulub impact would have created and carved flow valleys. It's quite possible that our Mississippi Valley may have been a flow carved valley from the Chicxulub impact. That's a strict guess on my part, friends. I don't have any geological studies that indicate that, but certainly an impactor this size, which made significant geological impacts that can be seen billions of years later on Mars. This sort of an impactor would have left similar erosion and devastation on the Earth. So as we're winding up today, Mike mentioned When Worlds Collide, George Pal's movie. When I was teaching astronomy as a full year course, we did an entire series of science fiction films called Space Exploration in Popular Culture. And we would show the movies in class, and I would pause them occasionally to help interpret them for the teenagers in my class. And it was always a very popular event when we had 12 to 15 films per school year. And if you have a chance, go on a streaming service, or maybe if you can pick up the disc on Amazon or something, take a look at When Worlds Collide. If you're interested in my Space Exploration in Popular Series movie collection, send me an email, and if there's enough interest, we'll get Scott to put it up on the Explore Alliance page, and you can have your own little film study And I have some study guides remaining somewhere from some of the films, and I can pass those along. Anyway, I'm hoping that you're out taking a look at the big comet. I hope that you're taking a look at your new copy of the book Star Mentor. I am working on a new book, Begin with Binoculars. But, as a full-time teacher, and it's after COVID, would you believe my astronomy presentations are more popular now than ever before? There's a lot of pent-up demand. So I write when I can, but I'll be here every week with you. And don't forget to keep tuning in and let your friends know, because we are going to come up on the International Measure the Earth Day. You can pitch in, take some measurements, help prove the Earth is round, help defeat the flat earthers. Prove the Earth is round, prove that the Earth is a sphere, prove that the sun is a sphere. We're going to do some really amazing things. And we're not going to use anything much more complicated than a ruler and a broomstick. And we'll explain how all that works in coming weeks, and we'll talk about Eratosthenes. But for this week, friends, we're going to go ahead and wrap it up. And I'm so glad to be back on How Do You Know for another exciting season. And if you have topics, things you've heard about in astronomy, in the news, in space science and exploration, gravity waves, or anything else, drop me an email at astronomyforeducators@gmail.com. And we'll be happy to look into taking up your favorite topic for a future How Do You Know show. Again, thank you to all the good folks at Explore Alliance. Thank you to my producer, Paul, and all the good friends at the Explore Studio. I'm Dr. Daniel Barth, wishing you clear skies. Thank you, everybody. Bye-bye now.